How's this? Better, better, better. All right. Okay, so we're going to talk about a topic that can be a little bit on the frightening side. Hi, come on in. We're just about to start here. We're going to talk about the topic of planetary defense, and it sounds pretty scary to begin with, and there are some scary aspects to it. But in the end, it ends up being, I think, a reassuring story. But as I say, there are some unnerving aspects to it. So we think of space as being essentially largely empty, the Earth hanging in an empty void. And if you travel vast, vast distances, like 93 million miles, you get to something like the sun. Or 240,000 miles away, you get to the moon. And of course, over great distances, you can come to planets like Mars and Saturn and Jupiter, but mostly emptiness between them. But that's not really the way it is. The solar system is actually full of many, many, many millions upon millions of small planetary worlds, asteroids, anything from the size of boulders to small planets. And there's just a huge number of them. And the fact that there are all of these out there has left their mark on the surface of the moon. You look at the surface of the moon and it's covered with impact craters. You can see vast sprays of hot pulverized rock streaking across much of the surface of the moon. Vast areas of the moon are fully covered in these impact craters. And some of these impact craters measure tens or even hundreds, or in some cases, thousands of miles across, testifying to some really violent events. And it's not just on the moon we see these across the surface of Mars and on Mercury, and even out among the icy worlds of the moons of the outer solar system. But strangely enough, when we look down from space on the Earth, we don't see a lot of those impact craters. They're very, very conspicuous for their absence. Now, if you look hard enough, you will find them. But why would we not see them here? What's going on? Do we have some kind of special dispensation from cosmic catastrophe? No, we don't. We just have a lot of erosion going on and plate tectonics, resurfacing the Earth. And so the Earth gets hit every bit as much as the other worlds in the solar system. We just clean up a little better. But again, if you look hard enough, you will find examples, like Meteor Crater in Arizona. This big hole in the ground is about a kilometer across. It was formed 50,000 years ago when an iron asteroid, and I'll show you a piece, if you haven't already held a piece of the iron asteroid, I think most of you have, slammed into the desert here and created this monster hole in the ground that is really, has everybody here visited Meteor Crater? Anybody not visited? Oh, you go see it. It is wonderful. It is amazing. It is awe-inspiring. So imagine if such an event were to happen today. It would be a really bad day. The shock wave and air blast would be immediately lethal anywhere within 3 kilometers of the impact. Within 5 to 6 kilometers, the pressure wave from that explosion would rupture your lungs and you would not survive. At 25 kilometers, you still have winds over 100 kilometers an hour. Severe to moderate damage to trees and structures for 50 kilometers out. Keep in mind, this is a small impact event. This is only 1 kilometer across. As we look out across the surface of the Earth, we see more and more of these impact scars. Highly eroded in many cases, but telltale in some of their, like you look at a ring-shaped lake like this. Manicouagan in Quebec. Here we had 2 impacts right next to each other. Strangely enough, they seem to be of very different ages, though. Probably the most famous or infamous of them happened on the edge of what is now the Yucatan Peninsula. This is the Chicxulub crater. And no sign of it exists on the surface today. The thing is completely buried in sediment. But Pemex company was drilling for oil and doing some searches. And as they drilled down, they noticed beneath the sediment the layer of bedrock. And as they started mapping that out, it formed this gigantic rock ring. And people started investigating it and dating it, and they found that it was 65 million years old, which matched perfectly the time for when the dinosaurs disappeared. And after further study, we realized that a 10-kilometer diameter asteroid or comet came barreling through the atmosphere, and the impact resulted in a 1 billion megaton blast. Now, the Hiroshima atomic bomb was 16 kilotons. So this would be somewhere on the order of 60-some billion Hiroshima bombs. Clearly a very, very disastrous day for the dinosaurs. The crater is over 170 kilometers wide, 8 kilometers deep. Debris flung out of this crater was just searingly hot, and it rained down over a large area of the Earth's surface, catching half the Earth's forests on fire. Because it landed, at least part of it, in a shallow ocean, it created tsunamis, thousands of feet high, rushing far, far inland. Huge amounts of dust and rock were launched into the atmosphere. The atmosphere chemically was changed, acid rain covering much of the Earth, and the sky was darkened for a long, long time, causing the temperature to drop, a long winter. So those dinosaurs that did not get fried by the event ended up dying coldly by starvation. And we've got pretty good evidence of this now. All kinds of lines of evidence showing that this event did in fact take out the dinosaurs. But there's a lot more. We can go back across the history of the Earth. The Verdefort Dome is 2 billion years old, 300 kilometers wide. So even bigger than the event that killed the dinosaurs. As a matter of fact, as we look across North America, we can find a number of these impact scars. This is not a fully complete map here. But these things can be a lot of fun, really interesting to go hunt down and to examine. It can kind of become an obsession. As a matter of fact, one of my favorite stories of this, I'm also an eclipse chaser. I go run around the world trying to stand in the moon's shadow for total solar eclipses. And back in 2001, there was an eclipse going across Africa. A bunch of us went to Zambia to observe a beautiful eclipse from a wild animal preserve. It was incredible. But after the eclipse, some of the guys in my group realized that, hey, we've read that there's a nice asteroid impact crater in northern South Africa. We ought to go try and find that. Yeah, let's do that. We get into our vans and we start driving without any clear idea of where the heck this thing was. And we're driving along, and you stop at a village and you ask, and most of the time they shrug, no idea what you're talking about. But sometimes they nod and they point in a direction. We go driving off. We get to the next village and they nod and they point in a different direction. We're zipping all around. Finally, the day's getting late. The sun is getting low. But we think we're in the right area. We think we're getting close. And all the hands have been pointing in the same direction now. And so we're driving along and we stop and we're near this kind of shallow depression. And we see bulldozers pushing trash into it. Oh, no. Is this it? Is this what we've driven all the way here for? And we're sitting there just kind of staring at it morosely. And then one of the guys in our group looks up and he sees this kind of flat-topped hill, like a mesa. That could be a raised rim. We jump into the van, so we drive on up there. We get up to the top just before the sun sets, and we look down into Swaying Crater. It's beautiful, beautiful impact crater with a lake down at its bottom. And there's even a plaque on the edge saying Eugene Shoemaker, the world's greatest expert in impact craters, was here, and he verified and certified that this is in fact a meteor crater. It is beautiful. It's an amazing thing. Quite an adventure. So we know that these types of events were bad for the dinosaurs. But what about for us? Is this still an ongoing problem? And I can tell you personally, it is. Back in 2013, we knew that a big asteroid was coming our way. It's called Asteroid 2012 DA14, about 50 meters in diameter. And we saw it as it was coming in and realized it was going to come close. It was going to come closer than the moon. In fact, it was even going to come closer than the satellites that give us our dish network. It was going to come skimming by, but it was going to miss it. And we were so pleased at ourselves with all our cleverness for realizing that we were going to be safe. And we all went to our observatories and pointed our telescopes to watch as this asteroid went flying by. And we're all looking off in this direction as the asteroid goes flying by, feeling all so smug. And at the same time, another asteroid, which we hadn't seen, came up from behind us. And it did not miss. It hit. It came in over Siberia, over Russia, and blew up not far from a city called Chelyabinsk. This thing was 20 meters in diameter. It came in at about 19 kilometers per second, or 69,000 miles an hour. It slammed into the atmosphere. And at that speed, hitting the atmosphere is like hitting a brick wall. The thing exploded with a 500 kiloton airburst. So again, many, many, many times stronger than the Hiroshima atom bomb. That's right. It blew up without breaking it to the ground. It exploded by, and we'll talk a little bit more about that in greater detail coming up here, but you're right. It exploded in the air, and, whoops, we'll leave it right there. And even though it wasn't right over Chelyabinsk, the blast wave caused 1,500 injuries. A lot of people ended up in the hospital, a number of buildings damaged. An even bigger event, Tunguska, occurred over Siberia in 1908. Brilliant fireball came down, this huge blast leveled thousands of kilometers of forest. The pulse, the shock pulse, was felt around the world. In fact, it traveled around the world twice. The skies over Europe and Asia ended up having spectacularly colored sunsets for quite a while and remained bright at night. This is probably caused by a stony meteoroid, perhaps 30 to 100 meters in diameter, 2 to 20 megaton air blast, happening over Siberia. Now just imagine, if you will, what would have happened if this had occurred 60 years later, during the height of the Cold War, when everybody here in the US and the Soviet Union had their fingers poised above the buttons. If there was all of a sudden a 20 megaton blast over Russia, how would the world have responded? Further events, like also in Russia, Sokote-Alin, 10 kiloton air blast. This is one of my favorite ones. They're not always over Russia, and they're not always really big. October 1992. October, it's football season. And we're talking about over eastern US. All of a sudden, it's nighttime. People are out watching high school football games, and streaking over several states, you have this brilliant, bright fireball. It is really well documented. People with their video cameras taking pictures of their kids playing football are all of a sudden taking pictures of this brilliant fireball streaking over the eastern US. In the meantime, a 17-year-old girl is in helping her mom wash dishes. She's actually a pretty happy girl because she has gotten herself her first car. Now, it's not a new car, it's a used car. It's a 1980 Chevy Malibu. But she loved that car. She was really happy to have that. She's sitting there helping her mom wash dishes, and all of a sudden she hears a terrible crash. Goes running outside to see the whole back end of her car completely crushed in. She is heartbroken, and she's looking around trying to see who hit her car. But she can't see any other vehicle involved. And then, looking more closely, she sees that the back end of her car seems to be crushed in from above. And beneath her car is a large, strange rock. They called the local university. They came over, took a look, and they said, hey, yes, this is a meteorite. And we would like to buy it from you. They bought it from her for a healthy sum, and she no longer had to drive a used car anymore. These are just a few examples. About 100 tons of meteoritic stuff comes in and hits the Earth every day, on the average. Then we have some big days, but on the average. 25 million meteors a day in our sky. Now, most of the time when you see a meteor up in the sky, the solid object that causes it is about the size of a grain of sand. But sometimes something bigger comes in. And when that happens, then you can get something spectacular. And about once every 10 years, something comes in big enough to create a blast the size of an atom bomb. Every 10 years. An asteroid or comet greater than 1.5 kilometers in diameter could result in a global disaster. So let's get some terminology down here. I'm throwing some words around here. Let's try and nail some of this down. So an asteroid is a rocky object in space. They can range in size from a boulder to a small planet. Some of them may be primitive material left over from the formation of the solar system. In other cases, they are fragments of worlds that have been broken up by earlier impacts. A meteoroid is a rocky object anywhere from the size of a small grain to a small boulder. So a meteoroid in space. Now, as an object comes in, entering our atmosphere at that high speed, it will leave a streak of light caused by the intense heat of its entry into the atmosphere. That streak of light is called a meteor. And if something survives that journey and makes it all the way to the ground and you can pick it up, then you have a meteorite. So a meteoroid in space, a meteor when it's coming down through the atmosphere, and a meteorite when you can pick it up off the ground. If a meteor is particularly big and bright, it'll change night into day, or it'll be visible during plain daylight. At this point, we call it a fireball or a bolide. And sometimes, instead of just having individual meteors, we have a shower of meteors. And in this case, what's happening oftentimes is we're passing through a trail of debris, oftentimes left behind by a comet. And in that case, you see a whole bunch of meteors seemingly to come from the same direction. Comets are very different, though they are related. In the case of a comet, you don't see it streaking across the sky like a meteor. It seems to hang there, rising and setting along with the stars. That's because it is far more distant. This is a giant ball of, well, we used to call them dirty snowballs, but now they're probably more accurately described as icy dirt balls. And as they get into the inner part of the solar system, the heat of the sun causes the ice to start vaporizing. You get trails of dust and gas coming out from them. They're very, who here saw Comet Neowise back, what was it, a little over a year ago? Beautiful, beautiful view in the sky. But again, these things are rocky and icy bodies in space. They can be kilometers across. Now, looking at the distribution of asteroids in the solar system, we find many, many, many millions of them. The vast majority of them are clustered in this belt between the orbits of Mars and Jupiter. And that's a really fine place for the asteroids to be. And we keep finding more. Over 3,000 asteroids are discovered per month, typically. Wow, there's a lot of them out there. But sometimes, with the motions of especially the giant planets, Jupiter and Saturn, and their gravitational tugs, you can stir things up in the asteroid belt, and some of the asteroids might fall inwards into the inner part of the solar system. And that's when they start becoming a concern for us. Then we start having the near-Earth asteroids, asteroids that can actually come close to or even cross the orbit of the Earth. So if we talk about, you'll hear people talk about an astronomical unit. That's the distance between the Earth and the Sun, 93 million miles. Near-Earth asteroids are defined as those whose orbits get them within 3/10 of an astronomical unit. And then the ones that we call potentially hazardous. These are the ones that have diameters greater than 30 meters and come within 5/100 of an AU. Near-Earth asteroids are actually fairly new in our understanding. The first one wasn't discovered till 1898. By 1950, we knew of 13 of them. That was largely because of the limitations in our technologies. By 1990, it had gone up to 134. What we're looking at here is the near-Earth asteroid Ryugu that was recently visited by the Hayabusa 2 mission. To put it in scale, I've placed it next to the Tokyo skyline. By 2012, we knew of 8,800 of these. And we're now discovering about 20 near-Earth asteroids a week. There are probably about 1 million of them with diameters greater than 30 meters. And we've discovered less than 1%. Like I say, there's some scary elements to this talk. Yeah, so several times a year, we will see an asteroid coming in that we have never seen before. And we see it coming in and actually coming closer to us than the moon. Occasionally, we only see them after they have passed us. That's concerning. You know, we live in a cosmic shooting gallery. This one right here is the near-Earth asteroid Bennu. It was recently visited by the OSIRIS-REx mission, and I put it to scale next to the mountain, the famous mountain Shiprock. You know, it's a mountain-sized world. If that came in at many, many thousands of miles an hour, it could cause quite a bit of grief. We talked about airbursts. Let's define that. So one of these objects, as it comes in, it's typically coming in at about 38,000 miles an hour. That kind of velocity, when it hits the atmosphere, can generate a whole lot of heat. And also, you'll have a big difference in the pressure between the leading side and the trailing side. That can result in the disruption of that object coming in, depending on what it's made of. The air gets heated very strongly and will expand in a giant, incredible shockwave thunderclap. Now, a stony type of object coming in between 3 and 100 meters probably won't reach the ground, but it will explode in the air. But again, that can be potentially very destructive, as the people in Chelyabinsk learned the hard way. Stony objects greater than 100 meters in diameter, though, can punch right through the atmosphere and hit the ground, resulting in an impact crater. An impact crater is typically 10 to 15 times the diameter of the object that formed it. Now, more than 2/3 of the Earth is covered in ocean, so there's a really good chance that when these things hit, they're going to hit the water. And when that happens, you can get impact tsunamis. That is potentially really destructive. And one of the really wild things is when we look at the surface of Mars, along the shoreline of where there was once a great northern ocean, we can see mega tsunami scars, where asteroids plunged into the ocean of Mars and created titanic tidal waves, thousands of meters high, rushing hundreds of kilometers inland. And we can still see those scars today. But these pose a very real threat to us here on Earth. But there's, fortunately, there's a good relationship between the number of potentially devastating objects and their force. So, Hiroshima atomic bomb style blast, we'll see that can happen about once every 10 years. Whereas an event that killed the dinosaurs is going to be on the order of once every over 100 million years. And we can just kind of show this another way. 1 meter impactor happens on the order of every 2 weeks. Whereas something that is on the order of Hiroshima-style bomb, every 10 years, something that will actually reach the ground and create a crater, a 100-meter diameter thing, every 5,000 plus, a little over 5,000 years, and worldwide destruction, every 100 million years or so. So, with that in mind, we want to figure out, obviously, how to protect ourselves from this kind of threat. And that's what we're all looking forward to seeing tomorrow night. But we have to keep in mind that the first step in protection is detection. You can't protect yourself from something that you don't know is there. And so we've got to have a good, clear view of what all is out there and coming our way. And so we're putting together a new generation of telescopes. Here on Earth and in space, to scan the skies, to look for these things that are heading our way, to give us the kind of warning we need. Now, one of the real challenges we face is some of these objects spend a great deal of time closer to the sun than us. They may only cross the Earth's orbit for a little bit and then spend the rest of the time inside. In that case, they're coming at us from essentially out of the sun. That can make them very difficult to see. So what we'd like to do is put a space telescope in orbit in the inner part of the solar system, somewhere around Venus, able to look out and see these things that may be heading toward us from inside our orbit. But all in all, this strategy is working. And we have already discovered instances of objects now that we have seen discovered in space as asteroids, seen them coming into our atmosphere as a meteor, and being able to pick up shards of them off the ground as meteorites. Or sometimes see them out in space and then see them explode over the ocean, or hear them explode over the ocean. So there's some good news. We've cataloged over 15,000 near-Earth objects. Almost all are greater. Almost all of the ones that are bigger than 1 kilometer in diameter have been found now. That's good. And most of the 300 to 1,000 meter diameter ones have been found. Only about half of the 40 to 300. Okay. Our goal is to find 90% of the NEOs over 140 meters in diameter during this upcoming decade. So currently, we don't have any known asteroid threats in the next 100 years. But then again, there's a lot we don't know about. So I give this talk a lot. I give it to people of all ages, including young kids. And it's not that I enjoy scaring kids. I don't. But kids know about the asteroids. They know about dinosaurs. They know why they don't see dinosaurs today. And so when I talk to these kids, I will sometimes ask them, okay, so imagine we have these wonderful telescopes, and you're looking through one, and you see one coming your way. It's coming right toward you. It's coming right toward your face. What will you do? What will you do? You're starting to understand how the dinosaurs might have felt. What will you do? I remember asking this in a 4th grade class. And one little girl raises her hand, and she says, hug a bunny. So that's not necessarily wrong, but I'm hoping we can do better than that. Unfortunately, we can, because the good news that I get to tell the kids is that, yes, indeed, for the entire history of life on Earth, we have been at the mercy of these rocks from space. For the entire history of life on Earth, these things have been raining down. There's a very good chance that several times in the history of the Earth, life has been eradicated and had to start all over again because of this. But the good news is now, for the first time in the entire history of life on Earth, we have the means to do something about it. We didn't when I was born, but we do now. So for those kids in second grade right now, congratulations. Pat yourselves on your backs. You timed it out just right. So what do we do if we see one of these things coming our way, besides hugging a bunny? First thing we want to do is we want to characterize it. We want to understand just what is the nature of the threat. We precisely nail down the orbit of this thing, so we know just when and where we're going to meet. And then we try to characterize the object itself. Asteroids come in different forms. They can be light, fluffy rock. They can be icy. They can be dense metal. They can be loosely held together rubble piles. What is the nature of the object that is going to be hitting us? That's something we need to determine. And to do that, we've used a couple of different techniques. Earth-based radar and robotic probes are both very useful. In terms of Earth-based radar, we can take what just through an optical telescope looks like a tiny point of light, and with these giant radar dishes, we can resolve them into their true nature. And we've been using, to especially good effect, the Goldstone 70-meter dish here in California, along with the Arecibo 305-meter dish in Puerto Rico. But as you may remember from the news recently, in 2020, after a series of hurricanes and earthquakes, the Arecibo dish failed catastrophically. And it is destroyed. We need to do something to replace this. We need this asset. But the radar is working wonderfully. We can see the asteroid Bennu, which was visited by OSIRIS-REx. We got our first view of it in terms of size and shape from this radar observation. We were able to create a shape model, and when we finally got there with OSIRIS-REx, we saw, hey, we'd gotten that pretty close. We're able to see these things in detail. This helps us characterize the threat. But one of the things you've got to be careful of when you start hearing about asteroids and the relative threats that they pose is they'll talk about this asteroid is twice the size of this one. But what does that mean when we say twice the size? Are we talking twice the diameter? If you double the diameter, then you're actually making the volume 8 times bigger and the mass 8 times bigger. So, but also change in composition. If you talk about a stony object versus an iron object, the mass can be tremendously different even though the diameters might be the same. But the basic idea here for us to save ourselves is not to equip Bruce Willis with a nuclear bomb and send him out there to blow it into dust. I don't care what your problem is, your answer is almost never going to be giving Bruce Willis a nuclear bomb. Instead, what we want to do is change the path of the asteroid, to bump it in a way such that instead of arriving at the same place at the same time, it either gets here early and passes by before the Earth gets to that place, or it slows down and comes in late. We want to change its trajectory. Now, even when we know that the Earth is going to be impacted, there's still enough uncertainty that we don't have an impact point. Instead, we have an impact path, what we call a risk corridor. And as we start shoving an asteroid, what that does is that starts moving the risk corridor across the surface of the Earth and eventually, you hope, off the surface of the Earth. But you see the potential for mischief here. Now, a fine example of all of this was discovered in 2004, an asteroid called Apophis, about 325 meters wide. And it's coming in close. And early observations said, hey, this might hit us in the year 2029. We watched and characterized that orbit very carefully and saw that, in fact, it was going to miss the Earth, but only by 31,000 kilometers. That's close. That's much, much, much closer than the moon. So in 2029, unfortunately, it'll be daylight here, but if you go over to Europe, you'll be able to look up in the sky and see this thing moving across the sky. I'm looking forward to going to see that. But a question came up, because as it passes so close to us, the Earth's gravity is going to tug on it and change its path. So what happens when it comes around again? And people started looking and seeing that 2036 might be a real problem. Well, again, we've been carefully monitoring its path, and we realize in 2036 it will again miss us. But this is one we have to keep our eye on. So the plan here, the way we're going to protect ourselves, at least initially, is this idea of a kinetic impactor. Take a spaceship out there, unmanned, no Bruce Willis, and have it moving at very high velocity and slam it into an oncoming asteroid. It's a pretty simple technique. We have the technology to do it now. But we need to make sure that we have sufficient warning time. If you do this a number of years to decades in advance, then a slight change in direction of that asteroid will build up over that time to a large distance of a miss. But if we only have weeks to months, then we probably can't hit it hard enough with a kinetic impactor to change its path enough. So we need that lead time. Another factor to consider in a kinetic impactor is what is the nature of the thing we're hitting? Is it a solid piece of rock, a solid piece of metal, a loosely held together pile of rocks? That'll make a difference in terms of how much of the energy of the spacecraft gets transferred to the actual asteroid itself. Now, we've had some success with this. We've tested this basic idea already back in 2005 when we had the Deep Impact mission slam into a comet. Now, the goal here was not to change the orbit of the comet. It was to dig up some of the stuff inside the comet, which it did very brilliantly. But we've shown that we can take a high-speed impactor and slam it into a quickly moving object out in space. But now we really want to test this technology out. And that's why we're all here. This is what's going to happen tomorrow, is we're going to launch the Double Asteroid Redirection Test, or DART. And this will be an actual test of our ability to do a kinetic impactor to change the path of an asteroid. We don't want the first time we try this idea out to be when we desperately, desperately need it. So it's going to go out and it's going to hit a small asteroid called Dimorphos. And Dimorphos is actually an asteroidal moon. It's a small asteroid going around a larger asteroid called Didymos. Dimorphos is an object we've never actually seen. We only know it's there because of its orbit around Didymos. It takes about 12 hours to go around. And as it goes around, it comes in front of Didymos, and it blocks out part of our view of Didymos. So if we're measuring the brightness of Didymos, we see that brightness dip every 12 hours as Dimorphos covers part of it up. Now, this impact is going to happen at a distance of 6.8 million miles from the Earth. We're not going to knock Dimorphos out of orbit around Didymos. We're not going to cause ourselves a problem that we don't already have. But what we are going to do is now be able to measure after the impact what that interval between eclipses is. Very, very precisely, within fractions of seconds. And so we will be able to measure very precisely how much we have changed the orbit of Dimorphos. To get an idea of the sizes of the players involved here, Didymos is 780 meters across. It's as tall as a large skyscraper. Dimorphos would fit inside a professional baseball stadium snugly. So that's the kind of things we're dealing with here. The idea is we have Dimorphos going around Didymos. DART comes in, and shortly before DART hits, it releases a spacecraft called Lizia Cube, developed by the Italian Space Agency. I think there was just a talk on this. And Lizia Cube is going to be our witness to this event because DART isn't going to be able to report back. Once it hits Dimorphos, it's gone. So Lizia Cube is going to be our witness. We'll have the impact, and Lizia will watch. And then from our observatories on Earth, we will then measure the new orbit of Dimorphos. Pretty cool idea. Yes? What speed? Let's see. I think that was listed here. Let me see if I got it. Do we have that here? That's a good question, and I don't have that down. Let me check on that. I'll check on that if you're here tomorrow. Yes, you. Yeah. No. Yeah, it'll be kind of we launch and it's going to be heading out. They're both going to be curved paths. So yeah, we don't do straight lines when we're flying in the solar system. Gravity doesn't let us do that. Yes. So we anticipate our impact in October of next year. Yeah. Okay. So what about other ideas, other techniques? You'll hear other ideas besides kinetic impactors being discussed. Okay, nuclear detonation. Not to destroy the asteroid, but to give it an especially big kick. If something really big is coming in, okay, that's probably not going to happen. We know the really big ones. But if something really big is coming in, or if we don't have a lot of lead time, and we need to give it a really big kick, then conceivably giving it a big shove with a nuclear detonation might be in order. Something else people talk about is essentially landing on the asteroid and mounting engines or mass drivers on it to provide thrust from the asteroid and actually change its path. Do we have the technology to do that today? No, we don't. But it might be an alternative, especially in the case of something really big. A gravity tractor is another idea. Send a big spacecraft out and have it fly in formation with the asteroid and use the gravitational pull between them as something to tug the spacecraft out of its path. Ion beam deflection and lasers vaporize part of the asteroid and cause that eruption of stuff coming off the asteroid to cause thrust. There's all kinds of different ideas that would be used in different cases. For most part, the kinetic impactor is going to be our best choice. But in special cases, we want to be thinking of these additional ideas to handle all the other eventualities. Of course, there are political implications. Who do you trust to do this? This has got to be an international effort, clearly. And so NASA has established the Planetary Defense Coordination Office, working with other governmental agencies here in the US, civil defense, as well as other international counterparts. Something we haven't really talked about yet, but is of great concern, are comets. These can be the most potentially difficult impactors to deal with because they have these highly elliptical orbits. They spend most of their time out far in the outer reaches of the solar system where we can't see them. Then they come swooping in fast and straight in, and we only see them. They only become visible when they are crossing Jupiter's orbit on their way into us. By that point, it's probably too late for us to do a whole lot about it. So that's concerning. And like asteroids, they can be kilometers across, they can be rocky, they can be icy, and they can cause great damage. The good news is that there are far fewer of them to worry about than there are asteroids. So while they present a significant risk, there are much lower likelihoods of encountering these. But they're not zero. Back in 1994, we watched as a comet slammed into Jupiter. Really exciting to watch. People with backyard telescopes were seeing one hell of a fireworks show. And just recently, in 2014, a comet nearly missed Mars. Mars was actually engulfed in the coma and the gas around the nucleus of the comet. And this happened right as one of our spacecraft, MAVEN, was entering orbit around Mars. And we had to kind of maneuver it around the back side of Mars as this comet came in to try and protect it. But we know that our rovers probably experienced incredible meteor showers in the skies above Mars. But for now, we're looking forward to tomorrow night. A spectacular event, a launch, right there. And we're going to test out this technology that we may use to be able to save the Earth. Yes? That is. That's DART. So, kind of a historic time. We're doing something really important here. This is one of the more exciting missions and one of the more meaningful for us. Thank you all.